Looks like we have a battery too.
Yeah.
All right.
Thanks. Can you do this every? Yeah. All right. I'll give you a key from that drawer.
Okay.
Okay. Here we are. Lecture number 2. Your homework is available, almost ready, so to speak. There are 4 exercises, and we need just a little bit more work on the second exercises. I'll get to that in a second. Once I connect the projector. All right, so we will be focused a little bit today on the homework one because we don't have a class on Monday. So your homework is due, I think, a week from Monday, or maybe we'll extend a few days, maybe not this Monday, but the next Monday, right? That's the 22, or maybe 23. But the fact that we don't have a lecture on Monday will put some pressure on how fast are you going to get to the material you need to know to do that homework, right? So I'm going to focus on the homework today, and then we'll catch up with whatever we need. So we don't have a class on Monday, it will be the next Wednesday. Right? So we were talking about, let me walk you through the structure of the course first, just a little bit. What we're doing right now, so this is module 1. You don't have to take notes for this. This is just a recap of what we are. What our job in module 1 is data processing, parsing, normalization into feature matrices. Then we have similarity or distance pairwise. That is to say, normally, once we're done with the feature matrices, an object, an image, a document, patient, email, whatever it is, it's going to look like that. It's a vector xi1, xi2, up to xi3. Once we process the data, that's how our data is going to look like. A vector of typically numbers, but there might be there some things like colors, which are also converted to numbers. If I want to represent the color red, I'm going to have one of these components being the component red, and that's going to be a 0, 1 thing. It's either red or not red. A big thing that I'm going to say now briefly, but then we're going to talk more about at office hours. If you have a component that is colored, right? And the colors are red, blue, green, yellow, and black. Naively, what students and sometimes even researchers do is to say create one feature, right? And say red is 0, blue is 1, yellow is 2, green is 3, and black is 5, right? Because that's a perfect encoding of the colors. You know the map, you know 3 is green, and you can convert 3 to green and green to 3. What is the problem of that representation? Suppose I do this. Suppose for a color, I map R, B, G, yellow, black into 0, 1, 2, 3, 4. Which is numerical values, right? Would be valid. I could load it in MATLAB or in Python. What's the problem with doing this? We call this a non-numerical attribute. This is called a categorical attribute or data attribute. Why is this wrong? This here is wrong. Why grouping a categorical attribute, maybe the city you live in, or the color, your car has, or the brand of the car. Why creating an attribute that says 0, 1, 2, 3, 4, it's not the right
I
thing
think
to do.
you don't need to have add categories for all of them. You just need to have n minus 1 because otherwise it's overrated.
Right, you're saying it's sufficient to have n minus 1 of them, but that's not wrong. That would be a little bit of redundance, maybe. I'm asking, why is this wrong?
You want to maximize sparsity?
That, again, would not be wrong, will be inefficient, perhaps. I'm saying there's some reason for which this is wrong, all the way in the back.
Because red and green, for example, it doesn't make sense that one, two, and one, that they are similar. You are doing the similarity.
I think you warm, but not the explanation is clear enough. Yes.
Maybe like 0 to 4, so 4 will get a higher weightage when like the 4 numerical value will have a higher weightage than the 0 value.
You also warm. She's saying 4 seems like a big number as opposed to 0. Why give to k, which is black? K, give it a big value, and R it's a small value. But that does not point exactly why it's wrong. It points to something that looks funny, right? Why some things have bigger values. It's not exactly why it's wrong, but it's a worm. It's like him.
The distance between blue and red is actually not 1. I mean, it's just a logical representation. There's no actual the difference between this implies that the difference between blue and red is 1, which is not true. So it's actually
Right, but 1 is a you also warm. He's saying, why define the distance between blue and red as 1 when I could define it as 5 or 15 or 25? But 1 is a normalized unit. If you like 25, you just multiply with 25 and you get there. Most algorithms will have no scalability issues. Well, logistic regression can multiply with whatever value you want. Yes?
Program read it as numerical, right, instead of categorical.
Right, so we'll read as numerical.
It becomes like continuous.
So why is it wrong? It's true. He's saying when you read, if you do this mapping, you load into your data, now your MATLAB is saying those are quantities, those are numbers, 0, 1, 2, 3, 4. That's true, but what's the problem with that? Why is that wrong?
Because it's discrete vectors, then there's nothing in between two values.
So 2.5 is not a valid color, that's what you're saying. That's a good way to, I agree, that's a problem, like 2.5, it's not a value. But we can, first of all, this is not a big problem. It is a problem, but not big. Second of all, we can impose to whatever algorithm we have to say, use integers, the 2.5, round it to the nearest one, if we want to avoid that, right? Anybody else? Yes.
While manipulating the numbers, we might come across a result where 1 is the sum of the others. Like, so we don't uniquely know if 4 is actually that color or it came as a result of an operation on the other colors.
But that's not necessarily wrong. Even if it comes as an operation, assuming we truncate things to be integers, that's what he's saying, well, they'll be valid integers. You guys are all warm, but nobody points out to exactly why this is wrong.
You can have a color which is a combination of the specified one. So these categories, you may say they are distinct, but there may be some colors you cannot point it according to a distinct value.
Right, if I have brown, which is a combination of red and blue and green, I wouldn't have it as red plus blue plus green. I would have it as a new category, number 5. Right, but is that, I mean, maybe I don't need brown to be red plus blue plus green necessarily, right? In terms of categories, you're right, brown is a combination of other colors, but maybe in general categorical attributes, I don't need this relation between attributes all the time, right? I mean, if I have the brand of the cars, you know, Ferrari is not a combination of BMWs and Audis, so that'd be fine. Can I do it for Ferraris and Audis and BMWs and Mercedes? Can I map them into numbers? That will have the same problem. Yes?
By coding this way, you assume the differences between red and black and blue, green, that they're the same. But actually, the distances are not the same.
How do you know they're not the same? Like,
I mean,
he's saying, why say the distance between blue and green is 1, and the distance between green and yellow is 1?
Yeah,
Maybe the distance between green and yellow is bigger, visually speaking. When you look at green versus yellow, maybe it's not such a big difference as between blue.
You're right. Especially when you consider the green differences between green and red are 2.
So you talk about visual differences. You look at two colors, If they have high contrast, you would think that's a bigger difference, and if they have low contrast between them, like yellow versus green, perhaps, would be smaller difference?
I don't know, but I don't think it makes sense to call it this.
That's another interesting explanation. It's warmer than the rest, but not exactly the one I'm looking for.
Leveraging on this. So colors are not a quantity, so you should not be giving a quantitative representation.
Right. That's the explanation I'm looking for, but why? Why mapping into quantities is wrong?
Because if you use something, maybe something like some regression or some model which actually sums up those things to give a result, that will completely screw your model.
Maybe. You have a...
If we form a feature matrix, then like, let's say a color has color like red and green, and another car has colors blue, green, and it might not have red. How would you write that? It doesn't have red, so you will write maybe a 0. Usually they write 0.
But that's assuming I need for a car 2 colors. I think in general categorical attributes, every object has only 1 color. So I'm not going to deal right now with the problem that what if a car or an object has 2 of these? How do I represent 2 or 3 of these as a set? I'm not. I mean that's an issue. But in that case, I wouldn't use this representation anyway. I'm not bothered right now with the fact that some data in my collection may have red and blues, and then I have to write both red and blue down. So that's a separate point. That's not what I have in mind. Yes. Correct. That is the explanation. We don't want to say that green is the average of blue and yellow here, right? So see, as a quantity, 2 is the average of 1 and 3, exactly in the middle between them. So if you plug it into any algorithm numerically, it's going to be, okay, green is halfway between blue and yellow. And similarly, green and yellow is halfway between green and black, because numerically 3 is the average of 2 and 4. So as quantities, if we plug it into any sort of algorithm, they're doing whatever, this is going to appear numerically as they have some sort of quantity representation that's scaled. As in, again, 3 is 1 away from 4, 1 away from 2, the average of those 2 things, which is not necessarily true for colors. Somebody here pointed out that maybe green is an average of blue and yellow, visually speaking. I don't know, or like if you average the pixel values of RGB components, you get that. But in general, categorical attributes don't have this property. Think about car brands. Audi's versus BMW's versus Toyota versus Mercedes. You cannot say Mercedes is halfway between Audi and BMW or something like that, unless you have some sort of quantity from the manufacturer, right? They have ratings, or they have, I don't know, RVU values for patients. If you have such a thing, domain knowledge, every disease, every procedure, medical procedure has an RVU value, which is a quantity used for insurance. Those RVU values are designed to have exactly a numerical representation. How important was it? But again, absent of such domain knowledge, do not map categorical features into one feature that is numerical. Instead, so this is wrong, instead we're going to take the colors and we make few columns here. We're going to say red, blue, green, yellow, black, and all of these are 0, 1. So they're binary. And with this, I could also solve the problem representing 3 colors if I want. If I really have a car that has 3 colors, I mean, that's unlikely. Who would paint this car in 3 colors, right? Then I could do that if I want to.
So
Okay.
how are you differentiating between these colors? Like, is it combination? I mean, how are you?
How do I do this?
Yes.
So I'm going to have few columns in my data set, and all of them binary. And then when I parse the data, if the car is red, I'm going to go to red color and say
Okay.
1, right? If it's not red, I'm going to put a 0 here.
What if in the data set that we have not seen yet, there is an instance which doesn't map to any of these columns of colors?
Right. If we have designed such a schema and we get a data point that doesn't have those, the safest way is to put 0, 0, 0, 0. because we miss that color, we don't have the ability to go back to our data set and add a column, say, okay, this car is brown. We didn't think anybody would paint the car brown, but we found one, right? What should we do? Well, put a brown column. You'd have to go through all the data points and put brown 0 to everybody else. So either you have a mechanism to fix all the data points, or you just put 0, 0, 0 is not all the colors I've seen. So it may be a new color that I haven't seen, or maybe a transparent car. Right? That's no, just kidding.
So this scheming works when you have less categories, say 5, 10 categories. What if there are in larger data sets where the number of categories is huge? How do you deal with it?
So 2 answers to that. Scalability of data representation and sparsity is a big area of study. It's something that we could take on a little bit in this course, but it's a huge problem. How do I deal with massive stuff? In fact, there's a research field that's coming up in the last 3 years. Extreme data sets. So as part of machine learning data mining, research community, especially big IT companies like Google, are concerned with not so much with the algorithms. We know how to do stuff very well, but how do you take that algorithms or that representation and use it on things that have billions of things in them, right? So that's a problem that you guys would have to study further beyond this class a little bit. We'll talk a little bit about it. The other answer to this question is, we only need to concern ourselves with the data that is given to us. Theoretically, we could have some categories that are infinite, right? Like coordinates or I don't know, locations. How many locations are there? Well, there's like hundreds of thousands of locations, right? You don't want to design a schema for all locations that there are on planet Earth. Instead, you look at the data set you have and only map the locations that are present in that data set. Maybe that data set is for Massachusetts. There's only like 10,000 possible locations, like towns and villages in Massachusetts. So you only use the schema for those 10,000. And then you back to his question, what if you have a data point later on that's not one of these locations, where you put zeros to them because it's not one of yours. Same thing in medical billing codes. The number of disease diagnosis codes is like 80,000. You can create a schema for 80,000 diagnosis labels. It's called the ICD-10 data set that all the hospitals are using now. But if you look for a particular, nobody does things for all the patients at once. You look for, say, radiology at MGH, right? And you work on that data set, few million patients. If you look the ICD codes, the diagnosis codes in that data set, there's only like 3,000 of them, because it's only radiology and it's only the codes that are used in Massachusetts. So you don't need to create a schema for all possibilities. You only need to create a schema for what you think you're going to have in your data set. Okay. Alrighty. That took much longer than I wanted to, but it's a good parenthesis. Categorical attributes map much better to binary things than to, but again, if you have the domain knowledge, if somebody tells you how important is a color of a car for selling it, and it gives you a quantity, red sells better, that's 100%, blue sells like 80%, then you could create a column with those values in it, because somebody tells you how important each color. Similarly, how severe is a disease, or how much insurance can pay for a particular procedure. Okay? So in some cases, colors or other categorical attributes come with domain knowledge. Here's what the values you should map them into. All right. So now that we have this representation, we need pairwise, which is that Kij, right? That is the similarity between xi and xj, or the distance between xi and xj. You're going to have to implement this for your homework. And we have the KNN classification that is supervised. So technically, this item right here, it's not part of our course. We're dealing with unsupervised data and unsupervised machine learning. This is clearly supervised classification, the kind of stuff that you would do in a machine learning course. How to train, how to test with labels and all that. And the data sets you have those labels, so you can implement it. It's one of the few instances when we need a supervised. We're going to tack a little bit into the supervised world, just to have a way to to evaluate our work later on. You'll see what I mean by that. This is pretty simple. It's the simplest classification algorithm, and not one that you want to use in practice a lot. In practice, people use a decision tree or a regressor or a naive Bayes classifier, something like this. But we're going to talk today, if we can, about this. So that's one piece of your homework. There's another piece, which, this is more like ML kind of thing, and this is more like DM. We're going to need to do some data analysis. And you're going to have a little bit of a scale problem in this, I think it's called Aminer dataset. It's not really scale, but it's going to be scale for people who do naive stuff. There's like 2 gigabytes of data, and if you're naive about it, it can take forever. But 2 gigabytes is not really scale in the real world. And we're going to do frequent items patterns. And here you're going to use something called Weka Explorer, I think it's called. So we're going to do a little bit of what that is, but you're not going to implement it. You're going to just set it up and use some package. And this is some, I think the algorithms are called a priori and FP grow. This is the typical homework one that's given in data mining, at least the data mining courses we've been teaching here. So if you look at the previous years, that's their homework one. You're gonna get a double homework one, sorry. It's gonna take a little bit more time. But the problem with this, it's the traditional way of teaching and learning data mining. The problem is, in reality, this is what you're going to use the most. If you go right now in industry and you have to do anything with anything, you're probably going to hit something with similarity and classification much more than transaction frequent items kind of thing, right? So I don't have a sense yet how long this homework needs to be, how many days you need, but we're planning for about 20 hours total load. So me and the TAs will figure it out how long it should take, and we plan to take about 20 hours. If it's longer than 20 hours, we'll push the deadline or cut some problem in it. All right, now I want to talk about, again, we don't have class on Monday, I want to talk a little bit about this, enough to give you a start, and will be some slides that if we don't finish something now, you guys can catch up with that. And I leave a lot of details up to students and office hours. I don't want to deal right now with what's the right way to implement similarity measures. I want you to struggle, try something, it doesn't work, okay, go to office hours, figure out why you're doing it wrong. A lot of implementations, programming language, packages, libraries will be completely up to you, and the TAs will help you with that. So that's where we were last time. We talked about similarity and distances, and we need to recap that a little bit and look at it. So what's up with similarities? What did we say? We have a dot product, right? So dot product. That's the simplest and the most default one, if you want. That is what I typically call Kij, is the product of xi times xj, and that is the sum of xid times xjd per component. This is the component. And we discussed last time why this is likely to be large if the two items have big values with big values and small if they're opposite. So it makes sense as similarity. This is very much a linear algebra way of thinking about things. So this is certainly a similarity, right? Because it's large when the two objects are similar and it's low when they are dissimilar. What else we talked about? I think we talked about Euclidean distance. So that will be, let's call it distance ij, was the sum of xid minus xjd square for all these. These are the features, these are the components of every vector, right? We could take the square root of it to be exactly right, but the square root won't affect much. This is a distance, because it's 0 when they are identical, and it's big when they are different, right? We can have something called city block. This may also be called Manhattan distance somewhere else. The names, there are quite a few distances that have multiple names. This is the sum of the absolute values. Might be called Manhattan distance. I'm going to check that up to make sure I don't give you a wrong answer. There's a generalization of those two, which is called Minkowski. It's the square root of some power r. That's a parameter of the sum of xid minus xjd at power r. Right? I think if I plug in r equal 2, I get what? If I plug in r equal 1, I got this, right? But to make it absolutely clear how it works, maybe we should put absolute values here. Is that the same as the Manhattan distance?
Yes.
That's what I thought. The names won't matter for this class, but I want you to have familiarity when you read something to know what those things are. What else can we do? There's a bunch of them. We don't want to do all of them, but there's hundreds of those things. One that might be interesting is the, well, let's write it right here. What is cosine? So cosine similarity, it's very similar to the dot product. How does that work? So that is the product, the dot product xi times xj, which we just defined here, right? Divided by the norm of xi, let's write this, the vector xi here, times the norm of xj. So what does that mean? It's a dot product xi times xj. The dot product is exactly this. Divide by the square root of, in here we have sum of xi squared. That's the norm of a vector. And this is sum of x, sum over all these, so let me put xid squared, xjd squared. Geometrically, those are the length of the vectors. If you think about this geometrically, this is my system of axes. Here's xi, here's xj. The distance from here to here is exactly square root of xid squared. Right? As a segment, what's the length of this segment? And in algebra, we call that norm. In geometry, we call it the length of the vector. Cosine normalizes with those two things. That doesn't matter so much how long the vector are, because it get normalized. If you do a little bit of algebra manipulation here, you'll see that if I extend these vectors or shrink them, preserving the direction, I get the same value here. No surprise what cosine means. It's a measure of what? When you heard the first time about cosines in secondary school, cosine was applied to what? Angles, right? Remember that? Cosine was applied to angles? That's why it won't matter if you shrink those two things. Cosine is simply a measure of how far apart they are. How long the vectors are won't affect the cosine. This is a big deal in information retrieval because they use this kind of measure for text a lot, for features that have been generated for unigrams and bigrams. But it's a good measure in general, very related to the dot product. Now, if your objects been normalized by row, that's another thing I want to touch upon today, normalization. When we talk about normalization of a feature matrix, let me draw it here. Here's the feature matrix. We had it last time, x1, x2 to x10. This is feature 1 up to feature d. So this is an object, right? This is x I1 up to xid. That's an object. When we talk about normalization, what, in general, what do we normalize? Which says normalize the feature matrix or normalize the data. What do they mean by that? Yes.
Normalize a column.
Column, right? So when we say normalize, means normalize a column. This is a feature. It's also called column or attribute, right? And typically when people say normalize, they mean normalize each column. So when we talk about data normalization, we mean take a column and do something with it. Just give me 10 minutes and I'll get to what normalization means for a column. But in here, what did we take to say we don't need to take into account the norms because the norms are the same? Right? If all my data points, this is a data point. This is not a column. This is a row. In feature matrices, rows are objects like patients or emails or web pages or images, and columns are attributes or features. Right? That's a very standard format. So this is an object. If all objects have the same norm, whatever that norm is, 125, I wouldn't need this, right? Because it's all divided with the same norm. So as a measure of similarity or distance, if all the values get divided by the same exact thing, it won't affect what I'm doing with that similarity, right? Of course, in general, objects have different norms. Long vectors will have big norms, short vectors will have short norms. What would it mean to say, I have all objects the same norm? Would that be normalization? What would I need to do to make all objects have the same norm? What would I do algebraically to this matrix? Somebody else, let's give everyone a chance to talk. So I want to point out the difference between doing something row-based, which should maybe create the same norms because it affects each object separately, versus doing something column-based, which does not affect in particular one object only, it affects the whole column, but not the other columns. There's a confusion sometimes in saying, if I normalize my matrix, do I get all objects to have the same norm? Is that true or not? Yes?
So basically a single feature doesn't dominate the entire result.
What?
So basically a single feature won't dominate the entire result.
Right, so my question is again, if I apply any sort of normalization, I didn't say what normalization is yet, but if I apply some sort of function to do normalization per columns, can I hope to have an effect of what the length of the vectors is, the vectors being the rows? It's not a tricky question. You can follow your intuition here. Is normalizing the columns going to give me vectors that are normalized, meaning the same norm on the rows? What do you think? No. I also don't think so. So I'm trying to prevent that confusion in saying, since I normalize my matrix, which is very common in a lot of data sets to apply normalization per columns, I've seen this saying, I don't need to do this, it's normalized now, right? The vectors have the same norms. No, that's not true, because we didn't normalize the rows, we normalized the columns. Okay? If we normalize the rows somehow, we have an effect per row, we could have something so that every row now sums to 1, or have the norm 1, for example. In linear algebra, we don't call these things normalizations. We call them matrix transformations, and you can apply them for rows or for columns, whatever you want. Linear algebra doesn't care rows versus columns. But when we talk about data, rows versus columns are very different things. Rows are objects, columns are features. So typically when you say normalize, you mean normalize columns. And that doesn't mean now that I can get rid of these things. So that makes this different than this. It's the same numerator. This one divides by 1 with everybody. That would be the same if those would be constants. Because again, dividing with a constant everything will not change the nature of the similarity function. But in principle, those are not constants. So then cosine is different than the dot product. In practice, it may achieve the same result if you use cosine as an input metric to your KNN algorithm, for example, or clustering. You may get very similar clusterings based on this distance or that distance. But they're not the same thing. Okay? What would it be geometrically, by the way, to normalize the vector to have norm 1? What would that look, if I am to look at a bunch of vectors, you know, I'm plotting here more vectors. This xi, xj, xk, so on and so forth. Geometrically, what does it mean shrink or expand all vectors to have norm 1? If I look at the data set after I do that, row-based normalization, what would I see?
All vectors have magnitude 1.
Which means all points are on a ball. In many dimensions, ball, circle in 2 dimension, right? 3 dimension is called sphere. D dimension is ball of, you know, C-axis, right? Okay. So if I do something to make all these norms constant, typically 1, but it doesn't have to be 1. Essentially means shrink all vectors to the point where they intersect that ball, and then all my points are now on a sphere or a ball in D dimensions. There's nothing inside, nothing outside. All the points have been geometrically sized to be on the ball. Many data sets are like that. They map all the vectors first to a ball. The biggest reason for that has to do with convexity. Balls are very nice things. If you think about a circle, I'm making a parenthesis here unrelated to homework 1. Think about a circle. If my points are on a circle, no matter how many points I have, no matter how many dents I have, if I draw lines between those points in the order of the circle, right, things like this, I obtain a convex hull, meaning it doesn't have concavities in it that runs through all the points, right? And if I don't do this, if I have points inside and outside, it's very easy to see how I can have concavities inside my data set. Convexity, it has geometrical nice properties and algebraically nice properties. We're not ready to talk about convexity today, but that's one big reason to make all points being there. That is, if it makes sense for your data set. In some data sets where we care about cosine, we can easily normalize the points because it won't affect the cosine between them, right? But in some other data sets, we don't want to normalize the images, for example. Now, intuitively on a data sense, what does it mean normalize a vector? So I've got an image, or a patient, or a web document. Here it is. Suppose I do some normalization row-based because I wanted the norm to be 1. Or the sum, maybe not, this is the Euclidean norm, but maybe I want the sum of xid to be 1. What would that mean for the data?
You give me equal weightage for all attributes. Right.
Not sure. So I'm talking about the row-based normalization, the one that you don't have to do. You do column-based normalization, which is the typical normalization for data science. But what kind of example would I like? Where would I do this? What kind of data point will have such a normalization like that or like that, this being equal 1? Yes.
Where it it's like a probability, or where the whole data set sums to?
Not the whole data set.
No, so particular row is mutually exclusive, and they all sum up to one.
Where would I want the components of a document or an image or a patient or whatever data objects I have, I don't know, cars, horses, anything. Where would I want those to sum to one? Where I want to represent the attributes as a probability distribution. For example, words occurrences in a document. I may not care how many times Virgil appears in that document on an exact count. It may be 3 times or 5 times or 100 times. If it's a long document, maybe 1,000 times. But that's not important. What I want to say, the occurrences of Virgil in a document, the word Virgil, it's a probability. Like what percentage of the words in that document is Virgil? Of course, those percentages sum to 1, right? Because if you look at the documents, it's based on words. If you sum up how many times you see that word, plus sometimes you see that word, plus sometimes you see that word, that's effectively the document length, right, in words. So if I divide by the length of the document, I get every word occurrence, it'll be a probability, right? And it sums to 1. In that case, it makes sense, because we don't care maybe the exact count, we care the proportion. Every time we want this xid, the feature values, to be proportions of the whole x, it makes sense to do some row normalization. Now you should be aware that row normalization and column normalization don't play well hand in hand. If you do this, you may have broken up whatever you did for a column normalization. Right? In that case, the column doesn't have variance 1 anymore if you do this. So typically you do one over the other, and if you need to do both, you have to think hard how you're going to do that. All right. The only one I want to put here extra, again, there's a lot of them. You're going to get a PDF and some slides, and there's Wikipedia tables with many, many distances. Let me put this one last, and then I'll make a comment about that. Jacquard. This is, I want you to think intuitively of intersection by the union. I don't want to put a formula because the formula, it gets implemented differently for different data sets. This will be different for images versus text. But the concept is the same. Intersection between xi and xj, right? That's what it means. This is still an ij type of thing. So that's a similarity. And this is xi union xj. Now, what does intersection mean? So this doesn't play quite perfect with numerically. We thought that the vectors here are numerical vectors now, right? What do the intersection look? I don't want to think in terms of numbers anymore. I want the common sense. What is intersection?
Similarity.
Right. But what intersect of what? What does it mean for 2 patients to intersect, to have a large intersection? 2 cars to have a large intersection, or 2 images to have a large intersection? What does that mean?
Identical features. Identical features.
Identical features or very similar, right? Maybe we can say colors are either identical or different. So in intersection sense, the colors means they have the same color. If they have the same color, that counts as an intersection. They're both red. But for some things like blood tests, we don't care to have the same exact value. We care to be in the same range, right? You know, all the blood tests or the medical tests come with ranges. This is super low, lowish, kind of lower, expected, normal, higher than normal, abnormally normal, and way normal, this guy gonna die. Okay? So like they have these ranges. All medical tests, blood pressures, temperatures, everything is within those ranges. So for this data set, you could say if that value is in the same range, counts as part of the intersection. If it's not, it's different, right? So it takes a while to think, how do I actually implement this formula for numerical values? Because you have to know, when do I need exact to count in the intersection? It has to be exactly the same thing, like for colors, right? For colors to be either they both the same or they different. For ranges, you're going to be like, if it's within epsilon of each other, if the two values are close enough, counts as an intersection. And union will count typically as how many non-zero or how many relevant values you have. So that's another thing you have to be aware. Typically, these data matrices have the same width. I mean, the data points all have, in principle, conceptually D features. But in practice, they don't. What's a trivial example of that? So, somebody else. What's a trivial example where the relevant information about the data set, it's not all the D features that conceptually they all there. Can I say that for images? That not all pixels matter? Well, it depends. I mean, there are images for which all pixels matter, right? What's a trivial example where there's a lot of features but only few of them matter? Yes?
Say if we have a data set of patients and what treatments are given, say one patient was not given a treatment. So we don't know if that feature was valid or not.
That's true in principle, but it's not in practice. In practice, you're not going to look at all the patients that exist. In practice, you look for a particular domain, like all the people who have broken bones. And then in there, you don't have that much of what you're saying. In there, most people have given the same x-rays, the same, those are called dense data sets. If I only look at the patients that have, say, bone problems or digestive problems, and there's 20 tests or 50 tests, typically you don't have a sparsity problem. I have a different example in mind that it's very canonical, sparsity.
For example, for handwriting recognition problem.
For what?
For handwriting recognition problem, the color of the handwriting doesn't matter. So even if it is black, if the number is written in color, black color, red color, it doesn't matter. The color of the number doesn't matter. The shape and...
You mean if I have digits written as a picture? You're saying a lot of pixels would not matter in there, right?
I'm saying that the color will not matter.
Yeah, but the color is not, for digits, the colors will not be features, I think. The pixels will be the features. And the feature values may include colors or not. So what you're saying is a different thing. It's take a color pixel that has RGB values and map it to a gray values or to black and white, because I don't care about the color. I only care if it's more black or more white. That requires a different transformation. Look through all the values in the matrix and transform all the values which are RGB values into black or white, if you want. I have a different example in mind where I have a lot of features, but they don't really matter that much.
User and movie ratings. So there may be like a million.
There are many people who haven't seen many movies. So although I have 1 million movies and 70 million users, that will be 70 trillion ratings. Most of them are non-existent because how many movies did you see? Right? I mean, maybe some people see a lot, but most people didn't see that many. That's a good example. In collaborative filtering, while the data set is huge, there's many missing ratings. But that's not the one I had in mind. Yes.
Maybe like you were collecting tweets with data, and you were have all the words to make.
In general, not necessarily with tweets. What kind of data have the problem that there's a lot of D's, but very text? In text, right? D is very big usually, even for unigrams. You get 10,000, 20,000 unigrams very easily. But every document will have only some of them, some of the unigrams, non-zero. Now, for some data sets, very, very particular, this may not be true. If I collect all tweets that have in there Donald Trump and immigration and that, tweets being very short, I'm effectively forcing those words to appear in them. And the tweets are what, like 7 words to 10 words, something like that? Maybe in some very, very, very particular data sets, the D is not so big, and most documents contain those. But in general, for text, even if restricted to a certain domain, take all the Wikipedia pages that are about education, you still have this problem. You still have a lot of these, but most documents only few values in them. So now, that's where this union comes into place. what do we mean by union? If naively speaking, everybody has D features. So the union is all D's, right? How many things are in a union? All D features. That wouldn't make much sense, right? Everybody has exactly the denominator D. What's the point? Again, every time you divide or subtract, divide or add a constant, you don't change the similarity notion. So don't bother with dividing with some constant. That won't make any difference. Why this union is not a constant? Say I take documents, and I want to say union of the features of the documents. Should I use all D? No. But what's the union of two documents is then? The words that appear either in one or the other. Now that's for words. I may have bigrams. There will be bigrams that appear one or the other, whatever I have. So to make sense of this is a very popular measure, but to make sense of it, you have to think first, what is my numerator? What do I mean by intersection of images? What do I mean by union of images or documents? And then depending on what you mean, you have to implement that formula somehow. All right. So that's the ones that I think are listed in your homework. I think those two are required. So you have to compute those two, and those are optional. Yes?
How do we choose among these formulas and checklists? Are we supposed to just all of these?
So when it says required, it means you have to implement both of them.
Oh no, I mean like when we use in order, like how do we choose among these which one to use?
So these are required, you have to implement them.
Yeah.
These are optional, that's up to you to try them or not. What do you mean, how to implement this formula?
Oh no, I mean like when we use these formulas and like modeling, so how do we choose which one to use?
So if it says, again, the homework will say those two are required, you have to implement them.
No homework.
Saying in real life.
Oh, in real life.
In real life.
In real life, you need some domain knowledge of what makes things more similar. So I say, if you, domain knowledge beats any sort of algorithm, okay? If you go to a doctor, and that can explain to you what makes two patients similar, and then you take that knowledge and implement it in a formula, that's gonna beat, most cases, what you can do by default. If I were to implement something on a data set that I don't know what it is, somebody gives me a feature matrix and I have no clue what it is, right? Where it comes from. I would use this Kij first if I believe there's some linear relations in this matrix. So something that's very sparse tend not to work with linear algebra stuff. But if I see a dense matrix, typically not so many features. So some features that are 150 features, not so many zeros in it. That would be my first guess, Kij, dot products kind of thing. If I see something extremely sparse, right, I can look at the feature matrix and see how many zeros are in there. 99% zeros. Okay, that's probably not so good. I would use something like editing distance or maybe cosine. But it takes some trial and error to figure out for my image data set or my text data set or my patient's data set, what is the distance that I need to use. Maybe add here edit distance. Sometimes this is called editing distance because it's the sum of, not exactly that, it's sum over the, there's a predicate here, sine of, let's call it something else, xid minus xjd. Let's call it difference. Not difference, that's not good. Same or not. So this is not exactly an editing distance, but if I take every component of it and I map it into it's either the same or different, that again requires me to know for colors, I may mean exactly same or different, but for numerical values, I may mean if it's smaller than epsilon counts as the same, if it's not smaller than epsilon counts as different. If I use it as a count, how many of ones I obtain here, how many components are different, then it's called an editing distance. And there is a version of it which is not sum, but is a max. So you can call it edit distance max. So instead of taking the sum of the distances, take the biggest difference xi date without the predicate, minus xj. So what's the biggest distance between the components? So one thing that needs to happen, you're going to have to parse some data and apply similarity distance to it. Now, this can be done with libraries. So I don't mean you have to do it manually. And for people who know their way around Google and Python and scikit-learn and MATLAB, this would be a second time of operation. If you know what you're doing, there's a script that even downloads the data directly in the format that you want. You just to find that script. There's a Python script. You don't even need the data on your computer. You press a button, downloads it directly as a feature matrix. Isn't that nice? Right? You need to find that script. And a lot of libraries implement distances. You just say what distance you want, and it does it for you. MATLAB has a function pdist that you put in the matrix, spits out the differences. Be careful with some data sets that this matrix, the Kij, is quadratic in the number of objects. So even though the feature matrix can be small, because it's n times d, if n is 20,000, and you ask for a pdist pairwise function, you get 20,000 square objects. That's 400 million. So be careful how you call those libraries. Now, optionally, you can implement this yourselves. This is hard to implement it efficiently. Implementing a similarity function that works on all pairwise objects. Implementing the function between two objects to say, compute the distance between object I and object j. That's very easy. But running an algorithm that computes all distances, all pairwise distances, which is n squared, or n squared by 2, because you don't want to, most of them are symmetric, so you don't have to compute it twice. You don't need 8i to j and j to i, right? This will be the same quantity, ij or ji. Now, running a program that does it efficiently, especially in terms of memory usage, that's not an easy thing. More laurels to you if you implement it yourself, but that's an optional thing. Most people would use a Java library, which is the most efficient Java. Python, R, and MATLAB will be slower and will take more memory. Java will be the ones that run the fastest. But for those two, you will do the best you can with libraries available. So you can download the data and parse it into some sort of feature matrix, even normalize it. I'm going to talk now about normalization. And then apply the similarity pairwise similarity function. So let's talk about normalization. There's two kinds of way to normalize things that are default and some other weird ones. Maybe here. So normalization. That is per column. So one is shift and scale. That is, the result is going to be between 0 and 1. When you do normalization, you have to look at all the columns. The very typical mistake is if you have two sets, training set and testing set, for example. I normalize just the training set, and I forget to normalize the test set, and then the results make no sense. Oh my God, what do I do now, right? All normalizations have to be consistent between all the data points that you're going to use. So there are questions there like, okay, if my normalization requires some knowledge of labels, for example, that's not going to be the case in here. What do I do later on when I get a test patient for which I can apply my normalization to it? So there are some mechanics that says if you apply this normalization, you're going to need it for future patients or future images. And you have to be able to apply it, because if you don't apply it, your algorithm is not going to work. So normalization always have to apply to all data points. How do I apply? I have a bunch of values, right? So I'm taking a particular feature f. So I'm looking at this feature f. And I get f1, right? f2. Those are the values for all data points. I'm only looking at one feature now. So this is the value for that feature for the first data point, second data point, third data point. How do I shift its scale to get 0, 1? Yes, somebody else. I mean, this is a 5th grade exercise. How do I get those values to be between 0 and 1? Divide by maximum will make the maximum 1, but not the minimum 0, right? Subtract the minimum first. Subtract mean, divide by max. So some formula, every fi becomes fi minus mean divided by the max. This maximum is the maximum after taking the minimum out, right? Because there's original maximum, but once I take the minimum out, the maximum has changed. If you want to preserve the maximum, that will also be the max minus mean here. So that the biggest value will definitely be 1, because there was a maximum, the feature value that was the max, now that's 1. And the smaller is definitely now 0, because the smallest was the minimum. When I take the minimum out, that became a 0. What's nice about this is that, of course, there's 0, 1. Did I preserve what? So the values themselves are not the same. They're now between 0 and 1. Did I preserve the ratios? Are you sure? Let's think about that. What would be the ratio of fi versus fj? 2 values, right? And now that ratio becomes what? Fi minus mean, right? Divide by mean minus max minus mean, sorry. Over fj minus mean divided by max minus mean, right? Of course, the denominators are the same. So this is what now? Fi minus mean divided by fj minus mean. Is that the same? Is fi by fj the same as this? No. But is it reasonably close? What did it take to say the ratios have roughly stayed the same? When is this reasonably close to that? Where minimum is not close to 0, is significantly closer to 0, smaller in absolute value than the f's themselves. Right? So if those f's are valued like hundreds, and the minimum is 1, this ratio won't be affected. 150 divided by 170 versus 150 minus 1 divided by 170 minus 1. The ratio will roughly be the same. It will be greatly affected if I have f's that are close to the minimum. Like say this f is 20, that's the minimum, and this other f is 500. 20 by 500 or 20 by 50 is not the same as 20 minus 20 divided by. So you gotta be aware of how many of those ratios have I changed. That's gonna be important for an algorithm like regression. Regression, it's all about what's the ratio between the features. That's what the regression coefficients control these ratios exactly. But did I preserve the order at least? The bigger values are going to be bigger than the other values. If fi was smaller than fj, after normalization, is fi still bigger than fj? Okay, so that's good. Yes?
So what are you going to do if that happens? If this normalization is not working?
Well, that's the normalization. That's the way it works. I'm not saying this has to be the same, right? It may be a good thing. Like maybe the original ratios were not serving regression that well, but the normalized ratio serves much better. So I'm not saying it's a bad thing. I just want you to be aware that if the minimum is far apart from FIs, the ratios remain roughly the same, or definitely the same for big values. But for smaller values, when FI and FJ are close to the minimum, the ratio changes. How about a different one, which is the Z normalization, I think it's called. Your statistics. Anybody knows what that is? What am I trying to get out of it? I'm trying, not normal distribution is hard to get. I have to start with a normal distribution to get a normal. But what I'm trying to get is, which is the standard. Not the normal distribution, but what out of normal distribution I'm trying to get. I want a mean of 0 and the variance of 1. So this is mean, that's variance. Now I'm going to let you guys figure out, if you don't remember what variance is, for example. There's a formula for it. And this class is not about statistics. So there's a formula for variance, there's an empirical variance, there's a empirical variance, how to measure that. All packages, Java, MATLAB, Python, have ways to compute means and variances. Mean is simply the average, more or less, right? So that's a center. I'm centering at 0, and now I have unit variance. You should also know that standard deviation is square root of variance, okay? So if I do this, I don't necessarily get 0, 1 values. Am I having a bound here for mean and max? I still take a column, and I apply by the way, how do I get this? What's the procedure to get 0 mean, and what do I need to do to get to do this? So that's the formula here. What would I have to do here to get that? I have to subtract the mean first, right? Because once I subtract the mean, what's the new mean now? 0, right? If I take a bunch of patients, I take everybody's age in this room. Suppose that average age is, I don't know, 28. It's not 28, 26, right? If I subtract everyone 26, the new average is going to be 0, right? And then? Divide by? Let's see. Do I have to divide by standard deviation or the variance? Huh? I don't know. I don't remember. I don't want to remember right now. I want you guys to figure out what is it. Now, as the result, one variance means one standard deviation, right? So in terms of the output, having variation equal 1, variance equal 1 means standard deviation equal 1. But procedurally, what do we need to divide with? So that's something you're going to need to implement. So not all data sets need to be normalized. So there is no theorem or concept or algorithm that says you got to normalize the features, otherwise my algorithm won't work. In fact, many algorithms are designed to be robust, typically decision trees and boosting decision trees. Maybe you have heard of forests or random forest algorithms. Those are so robust that it won't matter too much if you normalize or not. They are looking for patterns in the data by trying to separate data. So whether you normalize or not, they're going to find the separation point. Because all these normalizations preserve the monotonicity of the feature. Bigger values remain bigger values, smaller values remain smaller values. Algorithms that are trying to find, now imagine this thing is sorted. Algorithms that are trying to find some sort of threshold that says, with values smaller than this, do something. With values bigger than this, do something else. It won't matter if the feature is normalized. They're going to look at the feature array, and you're going to find that threshold, whether it's normalized or not. But algorithms that are quantitative in nature, like regression, and they're going to use the quantities themselves to add coefficients to them, multiply them, do something, that's going to matter a lot if the data is normalized or not. Algorithms that weight all the features the same need normalization, because a feature that's very big, imagine I have some salary income, that's like $120,000, right? Versus age, which is 20 to 30. Those numbers, 120,000 or whatever the salary is going to overwhelm in a quantitative sense a feature that's like 20 or 30 or -1, right? So it's good to know what algorithms need normalizations. We talk more about that in the machine learning class. But in practice, what people do, they do trial and error, right? They try it unnormalized, try normalize this way, try normalize that way, see what works. You know, that's what. And pedagogically speaking, while in production you don't want to do that, in this class we definitely want to do that. We want to try as much as possible everything to see what happens. So that's that. I want to talk a little bit about KNN just to give you an idea what it is. We're going to have to talk about it more on next week. But I want to give you a sense of what it is. You're going to have to implement this yourselves. So you can't use a KNN library. It's just a few lines of code. You have to write it yourself. So KNN. This is a very simple thing, okay? This is the simplest classification algorithm. How many people have heard of or know in principle what it is? Hands up. Okay, not too bad, about half. This is a unrigorous version of it, and we're gonna talk more rigorously about it later. Here's how it works. KNN, first of all, does no training. Isn't that nice? We don't need to train it, okay? Most algorithms, you need to train it, right? Like you heard the support vector machines, optimization, you need to train it. Neural network, you need to train it, right? Boosting, gradient, trees, and so on, you need to train it. Logistic regression, you need to train, right? This one doesn't need a training. It just needs to keep track of the training data. So it needs to keep track or access of training data. So it needs to have access to the training set, but it doesn't need any sort of procedure to train. And then, what happens when I get a test point or data point? Suppose I get a data point xi, and I need, this is a classification algorithm. So classification algorithm needs to make a prediction on given labels. So my sets, my points will have be patients, for example, and the label that I'm looking for is diabetes. Will be cars, and I'm looking to predict the color. Will be emails, and I'm looking to predict spam versus not spam. Will be images that represent digits, like you have in the homework, and I'm trying to predict what digit is that image in there, right? So this is a supervised algorithm that uses labels. So what do I do when I get a point? It has a parameter, k. So when you run KNN, you run it with a k in mind. Say k equals 10. So here's what I'm going to do. How that works. First, find the closest k training points. So it needs this k, and it also needs the similarity or distance function. Let's call that S. So algorithmically, conceptually, without worrying about the efficiency of the algorithm, what does it mean find the closest k training points to X? It creates a set, it's called a neighborhood set, neighborhood of X, which are the closest by distance, you know, by sorting all training set by the similarity value between X and whatever training point I have, or training set points. Let's call them, I think I want to be exact here. Let's call this Z. Sorry about this. Z is the test point, and X are the training points. X and Z. So I look at the similarity value which is available to me, or distance. I could use similarity to distance. I sort by that distance, and I pick the top K of that set. So that's how I create my neighborhood. I say, what are the closest training points to my Z? And if K is 10, that contains 10 points. If k is 20, contains 20 points. If 5, it's 1, it's only the closest in the training set. And then, that's one step. Predict a label that is the majority or average in set and Z. Now, these are training points, remember? The labels are known. Maybe the label are diabetes. So I'm going to know for each one of these 10 points if they have diabetes or not, right? Or if those are diagnoses, I'm going to know what diagnoses are there. Or these are images, right, with digits, representing digits. I'm going to know for each one of these 10 images what digit it represents. Because in classification and supervised, I know the labels for the training set, but I do not know them for the test set. That's my job, to produce labels for the test set. How many people are familiar with this schema? Training set with labels, which I learn, or I can train on it, and test set without labels, for which my job is to predict the labels as I learn the pattern on the training set. Hands up so I can see. Good. So that's a typical supervised learning mechanism, right? So what I'm going to do here, I'm going to say, okay, take those closest 10 points, and if the labels are discrete, like diabetes versus not diabetes, take the majority. See, is the majority of these people have diabetes or not? If the labels are quantities, I'm trying to predict somebody's salary, or somebody's age, or maybe building cost, for example. That's a quantity. It's better to take an average than a majority. So for quantitative, so majority is for discrete, average is for quantities. For quantities, it doesn't make sense to take the max. You look at K, suppose I'm trying to predict people's salary, and I found that for her as a test point, the closest by features are the following 10 people. Then I take the average of their salary, and that's the average I predict for her. That's KNN. Simple, right? You're going to have to implement it yourself. The part is the efficiency part. The KNN is very simple. The efficiency comes in here. Well, what does it take to find the closest K things? Right? It implies a sort. Do I have all this matrix computed in advance? If I have the similarity matrix computed in advance, the whole matrix, n squared, then this is a sorting. But if I don't have it, maybe I don't compute the similarity in advance, but I can compute it here on the fly. I can only compute it, see in here, I need to compute only the similarity for the z's, z against everybody, right? It is not n squared, because n squared means all points versus all points. In here, it's only z versus everybody, just n. That's rank, something that you have to struggle with during the homework. You know, how do you actually make it work? Efficiency will not be the primary drive for the grade, so be completely secondary. Our job here is to first get it correct and understand what we're doing, and you being able to explain what you're doing. Efficiency will be a very small extra part. If you take 20 minutes to do this, great, and if it takes 20 hours, you still get the points, okay? Like, even though that's massively inefficient compared to the same laptop, same data set, same algorithm, much faster. The primary concern is to get it done correct and understand what we're doing. Secondary is, okay, how fast you did it. The biggest expense in time will be your time that you're gonna have to spend on it. Now there is a version of each which I want to talk about. I did the lectures out of turn. This is supposed to happen next week on Monday, but I'm worried that the other part that I'm going to shuffle some slides for 10 minutes here that I was supposed to do today, I think that's easier for you to kind of figure out by yourselves, and this needs more explanation. That's why I swapped them. If I did it for the Martin Luther King Day, I would have done it in the proper order. What else can I do here? Suppose I want to do KNN, but I want to do it a little different. I still have the similarity or distance S function, and K is now a radius. I have a K, but K is not how many points to pick, 10. K is now some sort of range or radius on epsilon. How things change. There's no training like before. There is, you get a test data point, Z. The only difference is in the neighborhood. So find NZ, the neighborhood. What's the difference here? This won't be the closest 10 points or K points. It'll be what? All the points for which the distance or similarity is
lesser than the range.
For this would be all the points X in training for which similarity between X and Z is smaller than K. Now if that's distance, will be similarity is bigger than K, distance will be smaller than K. Because those distances will be, they are close enough, so smaller than, similarity is similar enough, so it's bigger than something. So this K is not now an integer. In here, definitely K has to be an integer. It's 5 or 10, or it would make sense to say find me the 5.6 closest neighbors. That's an integer. But in here, it can be any range. It could be 22.7, because that's the range I want to use. Now, what's the advantage in here? There are always exactly that many neighbors, right? If I set K equal 5, everybody's label will be predicted based on how many neighbors? 5 neighbors. In here, that's not true. In here, within a range, fixed range, one data point, this is my Z, might have quite a few neighbors, right? Because in that range, there's a lot of points. This happened to be a kind of a common case, common patient. There's a lot of patients that are very similar to it. While another patient, Z, maybe has no, within that range, there's no patient. Because this is an anomaly, it's a weird patient, right? It's supposed to be dead a long time ago, but it's still alive. And then, when you find similarity by a range, it says, I don't find any patient like this guy. I can make a prediction in that case, right? How can I make a prediction if I find no neighbor? So that's a problem in this case. Some predictions are based off huge density, much more likely to be accurate. If I have 300 patients that are similar to that one, I make an average or a majority, I'm very likely going to predict the correct label. While for somebody who has no neighbors or maybe one neighbor, I get nothing. I get a prediction that's not reliable at all. Well, what's the problem in here? In here, when I pick the closest 5 neighbors, I'm guaranteed to pick the closest 5, right? This is my Z. There's no question in here that's going to be the closest 5. The problem in this case is that for some example, the closest 5 might be reasonably close. So it makes sense to predict for them, because they are reasonably close. And then it's likely that if they all have diabetes, this guy Z also has diabetes. While for another Z, when I look at close 5, I find them very far apart. They're still the closest 5, but they're so far that the prediction based on these labels could be quite unreliable. In both cases, you have to deal with something. In here, you have to deal with this case. What happens if I'm looking for a range that seems good to me? I have to figure out that range, but it seems good, but I have no neighbors. What do I do? In here, I have to struggle with the other problem, which is, okay, I look for the 5 neighbors, but they're so far away, I don't think I can get a reliable prediction based on these 5, because they seem to be totally, like, here's the researcher, here's his area of study and stuff, Virgil, he's working on these things. Find me the closest researchers that are working on the same thing. I find one guy in Antarctica, and one guy in Japan, and one guy, it's like, do I really think those 5 people are all similar with Virgil? Right? Can I predict something? So in either case, you're going to have to struggle with. You can choose which one to implement, but there is a little problem in either one of them. Yes?
What if they have a threshold, like, for this case? So,
This?
For the first case.
You want to implement both. You want to have, I want the K ones, but with a threshold sort of thing.
Right.
You can try that. I mean, that's completely up to you. I don't want to get into details. Maybe we'll get into some details on Wednesday. But I want you to try out stuff, and if you come up with some mix of those things, if the neighbors are too far, I'm trying to find more, or I'm trying to threshold it, that's perfectly fine for the, I mean, you have a lot of freedom into how to implement those things to make it work. The data sets you have are easy. So the performance you get with KNN is going to be like 95% no matter what you do. So that's not a problem. I could give you some hard data sets for which you're going to struggle with our predictions, but the ones you currently have are easy, very easy to achieve with performance. Like digits, if you look for there's 60,000 images, so there are 10 digits, right? Per digit is about 6,000 images. If you look for the closest neighbors for an image correctly, you're going to get images that are almost identical with it. If you look for an 8 and you look for the 10 or 20 closest images to that one in the training set, you're going to get 20 images that are identical with that 8. All 8s, so it's going to be so easy to say, you know, all of them are 8s, so that one must be an 8 too. There's a 99.5% accuracy on KNN on that data set, by the way. So what I want to do now, I was hoping to have about half an hour, but clearly I don't time myself properly here. I have a new laptop. I don't know if it works or not yet. First time I'm trying to connect to a projector. Let's see if we can make it work. There is a part of the homework my laptop is not set up yet in entirety. The screen that doesn't really stay, right? Oh, we got something. Well, I don't know why it's so green. I won't deal with that now. Sorry about this. I'm going to have to set it up. But for what I need to show you, it won't matter green or blue. Apologies for how it looks. So in homework 1 here, what you're going to have to do for the first problem is a large data set with simple questions. Once you parse the data set, how many authors I've seen, how many books, how many this and that. It's just a way of parsing and produce those counts. It's not a trivial homework because it takes time to do it right, but in terms of intellect, it will require almost no thinking just to parse it right. And we have maybe more specifications about this today, but that the biggest part there is parsing this data set. That's the problem. And once you parse it, you're going to have to answer those questions. The second one is the slides that I didn't have time today. I'm going to use 5 minutes to go through the slides. You may have to look at them yourselves, but I'm certainly going to go over them on Wednesday. These have to do the reason this is not so hard is because you're going to use this Weka Explorer. So you don't have to implement it yourself. It has to do with mining association rules in a transaction data set. You do have to parse the data set and feed it into Weka Explorer and press the right buttons in there. But it's not that super complicated. I'm assuming people know how to use a GUI with buttons in it. These two data sets, one is images, MNIST. The other one is text, 20 newsgroups. They come with labels. Some are multi-label. Some of these article 20 news groups have more than one tag. They have politics and sports in them. So right there, when you create the neighborhood sets, you're going to get each article having more than one label. So when you create an output label, you have to deal with sets of labels, but not hard. So for those two exercises, the last two, you have to, first one requires parsing normalization, creating a feature matrix. Again, you can use a library, you just have to find which library you can use in there. There's some code that does all of it for you. Typically Python, scikit-learn, this would be the easiest by far. I'm not asking you to use Python. I'm saying if you want to do this fastest way possible, Python is the thing. And the second part is implementing the KNN classification, which is once I have the feature matrix, train test have to be a split. I think some of the data set come with a split. It says train set, test set, so obviously use the training set as training. If it doesn't come with a test set, for MNIST I think, you have to split the test at about 10% of the data yourself. Make sure you split it per category. So you don't take 10% at random from 60,000 images. You take out of all digits that are 2, all images that represent a 2, 10% out of that. Out of all images that are 3s, 10% out of that for testing, right? So you want to take 10% of each category, not 10% overall. Okay? So I think that doesn't come with a test set, so you have to create a test set yourself. And then you implement the KNN algorithms. You should get very high performance for both of them. That's the homework. Me and the TAs are still working on it, but you can certainly start. You're gonna have to use a password to download the data from here. There's a link in there, and it is the data sets. The password, I think it's mining data in one word without capital letters, mining data. Probably possible, yeah. Now, what did we miss? We only have 1 minute, so we clearly cannot do this. I don't know how many people are familiar with the notion of a transaction data set. It's not really images or text, but it comes like this with some sort of tags or transaction concepts, and every row has to do with, in row 4, I've seen these 4 things. Okay? You can imagine data sets, many data sets written that way, typically database records. You know, here's a row, here's what happened in that row, here's the attributes of a. You can imagine this take a data set like images or text and have the document number 4 contains the following words in it. But it's slightly a different format than the feature matrix we used to. What you're gonna see here in these slides, there's a lot of blah, 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 blah that we can skip. Right? I mean, we'll talk about it on Wednesday. I don't mean to skip it. The interesting part related to your homework are 2 things here. So there's some nice images of, for example, how do you think of these association rules and what makes an association rule more popular. There is a way to count how important, how frequent is an association rule in here. But that count is simply like how many times I've seen it. There's nothing magic into how to count it. The things that we're gonna need on Wednesday for how to do this, there is a soft version and the actual version. How do you mine the association rules? So the first thing we need is this a priori algorithm. This has to do the following. These are the individual terms with counts. How many times I've seen in each transaction beer or bread and cola, so on and so forth. This, it comes to how do I create from unit or unigram based counts, how do I detect bigrams? If I don't want to parse the text for bigrams, or in here I can't because this is a transaction data set, I'm going to say, okay, combine beer with bread because they have high counts. If they have high counts, I get this now second level association rule. But then I have to count to see how often that happened. The fact that they have high counts independently doesn't mean they have high counts together, right? All these algorithms have a pruning mechanism to say, once you produce a bunch of candidates, you have to count them to see if you actually see them in your data, and if you don't see them enough, kick them out. So all this algorithm has a phase that says, if the count is too low, take it out. So this a priori algorithm produces candidates based on the previous counts and then prunes them to say everything that has low counts, remove them. But then it moves further. Now the next step will be bread and beer and milk. And then again, if it has low counts, take it out. You don't have to look at these if you want to wait for Wednesday. But if you want to do the homework now, this will only take you about 10 minutes to figure out what you need to do. One more thing. How this actually happens in reality, which makes it much more interesting, is this FP growing tree. So this sounds very fancy, but it sounds extremely simple in practice. What it does, it says, okay, I'm going to organize my transactions here. I replace bread and butter and milk with X, Y, Z. And I'm going to organize it in a tree. And how to organize this in a tree, it's extremely simple. I look for the most frequent thing. I put it here. Right. If I see a transaction ZX, X becomes a child of Z. Right. And then I see another transaction that starts with X, maybe here. X becomes a child of the root. XR, XR. I mean, this is what you see is what you get kind of thing. This tree will make it much more efficient than the a priori algorithm, because there is a two-stage process. First, compute all those counts and everything you need, and then figure out the tree. That is how this is done in practice. Now with the a priori algorithm, that has too many loops. It's based on this. Now, you don't have to implement this, because you're going to use this Weka Explorer who implements it for you. Okay? But you have to know what it is. You may get this question in an interview. How people build an FP growth tree. It's extremely simple. Compared to algorithms, when you talk about red-black trees, who takes algorithm with me? Yeah, red-black tree is going to be much more complicated than this stuff. But you may get that question in interview, how do you build an FP growth tree? And you have to know how to answer it, okay? Because if you don't know it, they're going to be like, okay, you didn't go into the first lecture of data mining. Okay? So this is the problem that says you use Weka Explorer to do it. If we have an exam, there may be a question, nah. All right. Happy Martin Luther King Day. I won't see you on Monday. The first office hours are tomorrow, Thursday. Okay? We have office hours in the evenings, about 5:30 p.m. or so. There will be tomorrow. We won't do anything on Monday. The next class will be on Wednesday.
Where next?